So, welcome to the 25th lecture. So, this is again the continuation of the previous lecture, that is Introduction to Error Control Coding. So, in the previous lecture, we saw the definition of error control coding. In case of error control coding, the channel will be to overcome the noise or artifacts introduced by the channel. The transmitter will introduce some additional bits, or they are called as redundant bits, to the data to be transmitted, so that even if there are errors introduced later in the channel, those errors can be overcome, or the data can be detected whether there is any error or not. And also it's possible to correct the errors at the receiver. So that's the main objective of adding redundant bits to the data to be transmitted at the transmitter, so that those errors can be detected, or it can be corrected at the receiver. So that's the main idea of error control coding. So we will continue the discussion further. So here we will see specifically why do we need to do the error control coding when we consider a communication system. So here, the first point, severe transmission problems. So when the data is transmitted by the transmitter through the channel to the receiver, it is possible that the transmitted data may get reflected, because between the transmitter and the receiver there is a channel. If you consider a wireless channel, the transmitted data, when it propagates from the transmitter to the receiver, may get reflected by different obstacles. For example, maybe some trees or mountains or some buildings in a city, etc. The transmitted information may get reflected due to hitting some surface, maybe a tree or a mountain, etc., and it may get diffracted, bend from the obstacle, and also it may get scattered to different as different particles. So altogether, these are the uh, combined effects of a larger phenomena that is called as multipath fading. So due to multipath fading, the transmitted information, when it reaches the receiver, this overall signal strength may get reduced. So as a result, at the receiver, it is possible that receiver may not be able to receive or clearly understand what was transmitted. So it feels that information as something error. So if there is uh, redundancy in the transmitted data, then with the help of those redundant bits, the receiver can try to understand what was transmitted. That means error detection or error correction is possible. And also a scenario like low signal to noise ratio. So even when there is a low signal to noise ratio, the receiver finds it difficult to decode the information. So if the data is transmitted with some redundant bits, that is, if the channel coding is done, then the receiver will have some hint of how to decode the data. Similarly, in case of satellite communication, when we consider a forward channel refers to the data transmission from the satellite to the Earth station. So since the satellites have limited power, that is a forward channel, that is what we call it as a forward channel. Since the transmitter, which is a satellite, has limited power, it cannot transmit. I mean, the again we have the same scenario of low signal to noise ratio. The transmission, even though it is transmitted by the transmitter, since the distance between the satellite and Earth station is too much, then the receiver at that station may not be able to receive or to understand what was transmitted. So in all these scenarios, we need to have the error control coding setting. Otherwise, it's difficult for the receiver to understand what was transmitted. Okay, those are the scenarios exclusively for a communication system, especially for a wireless communication system. So altogether, based on our discussion of why do we need to have error control coding, the overall idea here is we will be adding some redundancy to the data to be transmitted. So by doing that, is there any price we need to pay? Of course, we have some data, we add redundancy, that's all fine. Do we have to pay some price for this? Yes. The main thing is when we add more bits or redundant bits, we need to transmit more number of bits. That means we need a higher bandwidth because bandwidth is a precious resource. We need to have a higher bandwidth to achieve this redundancy. Next point here is increased complexity. So if we use the error control coding, we will be basically increasing the complexity at the receiver. We are making the receiver more complicated. The design of the receiver is more complicated because receiver has to detect the error and then it has to correct the errors and so on. So the complexity has increased at the receiver side. Even at the transmitter side, we need to implement complicated algorithms to encode the data. So the price to be paid for redundancy is, or by adding redundancy, we have 2 points here. First one, by adding more bits, we need to have higher bandwidth. That is a burden. And also, we will be making the system more complicated or more complex. But on the other side, even though there are two limitations or two overheads involved, the what's the benefit we achieve by using the redundant bits? The receiver will be in a situation to detect the errors or sometimes to correct the errors. That's the benefit we get. To get that benefit, we need to overcome these two scenarios. That is, we need to have a higher bandwidth as well as we need to compromise with the complexity. That means we need to accept that there is complexity involved. Okay, now we will see error control coding types of error control coding. The error control coding can be categorized into two groups basically. We will see what are the two groups or two classifications of error control coding schemes. Before going to that, we will also see another scenario here. In some cases, we do not appoint any error control coding schemes when it is more suitable. For example, a transmitter sends some data to the receiver, and the chances of errors are very less. In that case, the receiver need not have all these complicated error control coding schemes. Instead, the receiver can just ask for retransmission of the data. If it finds that there is some issue or if the receiver cannot receive the data within some particular time, then it just need to ask for retransmission. Then the transmitter will retransmit the data as mentioned here. So that process is called as auto repeat request or ARQ, auto repeat request. So in this case, there is no checking for errors or no correcting of the errors, nothing. The transmitter transmits the information and receiver, if it cannot receive it within a particular time, then it will ask for retransmission. Again, transmitter will retransmit, the receiver will try to receive it. If the receiver cannot receive within a particular time, then again ask for retransmission. So this process will continue until the receiver will successfully receive the data or the number of attempts for retransmission is reached, the maximum number of attempts are reached. Until then, this process continues before declaring the data is successfully accepted or there is error in the system. So that is the very simplified version of communication system between transmitter and receiver. there is no error control coding involved. But we are talking about the scenario where we will be using some error control coding schemes. So there are two classifications here that we will see in the next slides. Okay, so for some applications, the application demands a severe time constraint. So there is no retransmission possible. So that means in the previous case, as I mentioned, that is ARQ, the receiver can just ask for retransmission without checking whether there is error, or it'll never try to overcome the errors or try to correct the errors. So that is possible because the chances of errors are very less, and also the communication is more relaxed. There is no time constraint involved. So the receiver can ask for retransmission any number of times. But most of the times, or for some applications which are called as time critical applications, the transmitter cannot uh, keep retransmitting. The transmitter will transmit once and the receiver will receive the data. Maybe if there is error, it cannot ask for retransmission. It has to deal with that. The receiver has to identify if there is error, and it has to also solve those errors. Where the error was, it has to correct those errors, because the time involved is very limited. It cannot spend its time asking for retransmission and so on. So in that case, the receiver should have the ability to detect the errors as well as correct the errors. So such systems, or such system of error control coding where the receiver can detect as well as the correct the errors, is called as forward error correction, FEC. Okay, so this is exactly what we do in the error control coding: detect the errors as well as correct the errors. Why the receiver has to detect and correct the errors instead of just asking for retransmission as done in ARQ? Because there is a time constraint involved. The receiver cannot spend its time doing asking for retransmission. It has to, as the data is received, it has to identify whether the data is all right, or if there is some issue, it has to try to recorrect by itself. So this is the idea of forward error correction in error control coding. So where this is more suitable, it is appropriate for delay sensitive or time critical application. For example, broadcast in a TV. When the data is transmitted through the TV station to our home, the receiver should have the ability to detect the error if there is some video frame missing, and then it has to correct it. Okay, now we will come to the formal discussion here. What are the two classifications, as I mentioned earlier, with regard to error control coding? The first classification is called as block codes. The second classification is convolution codes. So in case of block codes, we have a stream of data. This stream of data is divided into different blocks. For instance, we may have a long data stream such as 1, 1, 1, 0, 0, 1, 0, 0, 0, 1, and so on, and so on. So this is a long stream of data that has to be transmitted. So in case of block codes, it will pick a limited number of bits, for example 4 bits. A blocks of 4 bits are chosen, for example the next 4 bits and the next 4 bits, and so on, like this. And then it will convert these data bits into an encoded sequence, and next the next block of data bits into another encoded sequence, and next the next block of data bits into another encoded sequence, and so on. So basically it converts the data stream into block of data, and then on each block of data it runs the encoding operation and performs encoding. That is the idea of block codes. So here we form the message blocks as shown here. In this example, we consider 4 bits as one block. So the definition is here. We consider a k-tuple binary message block. K-tuple indicates k number of bits. So k number of bits, in this case k is equal to 4, and it is converted into n-tuple code words. So n number of bits. So 4 number of bits are encoded as more than 4 number of bits, maybe 5 number of bits or 6 and so on. For instance, when we see, or when someone says 7,4 block encoding, that means 4 bits of data, k is equal to 4 here, is converted into 7 bits of coded sequence. N is equal to 7 here. So how do we generate these 7 bits from these 4 bits? That means we will be adding 3 additional bits to this data block. So these 3 bits, what we add additionally, they are called as the redundant bits. So altogether these 7 bits becomes the encoded sequence or code word. So how do we add these 3 bits additional bits? By doing some operation on these 4 bits of data. We run some algorithm on these 4 bits of data and generate 3 additional bits. So 4 plus 3 becomes 7. So we form those 7 bits. The next classification, and this process will continue on all the code words. That's the idea of block codes. Then the next case is a convolution. In case of convolution codes, we, instead of considering this kind of blocks, we consider a sequence of data, and then we use a memory on each bit of data, and we generate the output, that is encoded sequence. So here when we generate the encoded sequence, the bit what we have in the encoded sequence, that depends on the current input and the previous bits or input bits. So to do that we use a memory here. Memory can be a shift register. Okay, so any output bit generated depends on the current input as well as the previous inputs. Those two are combined in the memory and then gives out an output that becomes a bit of the encoded sequence. So in that way we generate a more number of bits, or as many number of encoded bits we need, we generate that. For example, in case of 7,4, when we consider a convolution code of 7,4, we have 4 number of data bits, 7 number of encoded bits. But those out of those 7 bits, how do we generate those 7 bits? That will be decided here. We consider the current input, previous input, we run that in a memory, and we have some logic in the memory. Based on that logic, we will be having those 7 bits as output, that is an encoded sequence. So here a sequence of blocks are considered. Instead of dividing the data into different blocks, we consider a sequence itself. Okay, so that is the idea of convolution codes. So again we have different classifications here under block codes as well as under convolution codes. That's a different type we have. Okay, the overall the key idea of error correction is you are giving the power to the receiver to detect the errors and do the corrections by itself. So there is no retransmission required, because the receiver has the ability to detect the errors and also it can correct it by itself without the help of the transmission or transmitter again. Okay, so the major categories of error control coding or forward error control coding, specifically that because the receiver has the ability to detect as well as correct the errors. Linear block codes and convolution codes. So under linear block codes we have the two Just two are mentioned here. One is cyclic codes and Reed-Solomon codes. Some of these codes we will study in the upcoming lectures. And also under the case of convolution codes, we have turbo codes. So on. Another classification is a minor classification, that is linear codes and non-linear codes. So in case of linear code, what happens is we have in case of linear codes, we have a special property that when we add any two linear codes, we generate a third code. That third code is also a part of the previously added linear codes. So that is what here is the definition. Linear codes have a unique property that when any two code words of a linear code are added. So basically when we talk about adding, we will be using a mod 2 addition. The third code or the new code after the addition, what we generate is produced, that is also a code in the linear codes. I mean what we add initially, it's a part of that. So that is the case in case of linear codes, but that property will not hold good in case of non-linear codes. We will see some examples later. Okay, then we have another term here, that is parity code, detect the errors. So parity code is the very simplest scenario of uh, detection of errors. I told you many times that the receiver, in case of error control coding, receiver has the ability to detect the errors or sometimes correct the errors. So parity code is a very simple scenario, or the simplest scenario, that says how the receiver can detect the errors. We will see some examples here. So first we will see classifications of parity code. So there are two classifications. One is even parity, other one is odd parity. So in case of even parity, what happens is we have some data bits. We need to add some additional bits. So how do we add those additional bits? That is by using this equation or this mathematical relation. So the additional bit added, which we call it as Q in this case, is equal to the summation of all the data bits that we want to encode. So when we do the summation, we will be using mod 2 operation. That is in case of even parity. So what do we get here when we do the mod 2 operation? Maybe we get a 0 or 1. So that particular bit, a 0 or 1, that we will be adding to the data bits or attaching to the data bits, and we will be forming the encoded bits. We will see here itself the help of an example. And the other case is odd parity. So in case of odd parity, we will be adding additional bit to the data bit when we do the encoding. So what is the additional bit we need to add? That its value is 1 minus q. So q value comes from here. For example, q value will be either 0 or 1 because we are considering the mod 2 operation. So if it is 1, so 1 minus 1, 0. If it is 0, it becomes 1 in case of odd parity. So we will see maybe the case of even parity. So we will see the case of even parity here. The data we have is this 10110. We want to encode this data, or we want to convert it as a code word. Then how do we do that? How do we do the channel encoding on this data? Using even parity technique. So basically even parity says how many number of ones are here. Is it even? Okay, let us see here. How many ones are here? There are three number of ones. 3 ones, right? Is it even? 3? No, 3 is odd, right? So we have to convert it into even number of ones. So we need to add a 1 here. That is what is done here. That's the overall idea. But Okay, we will see based on this definition itself. So this is the given data. We want to encode this using even parity. How do we do that? We need to attach some additional bit here after the data bits. We need to add some additional bits here, or attach or append. How do we do that? We need to compute Q value here. What is Q value? Q value is a summation of all the data bits using mod 2 addition. So let us do. Here we have all the data bits. We will add them using mod 2 operation. Mod 2 is basically XOR operation, exclusive OR operation. So 1 XOR 0 is 1, 1 XOR 1 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1. So the Q value what we generate is 1. So that value is added here. I mean attached here along with the data. So that becomes the code word using even parity. So in case of even parity, we have the data. How do we convert it into encoded sequence? You do this operation on this data and you will get a bit, maybe 1 or 0, that you attach here. So these are basically the data bits shown in black color, and this red color is the parity bit that is attached here. So the overall meaning here is, in case of even parity, you check, are there even number of ones? No, in this case no. So you make it even. So you have to add one more one here. So how many ones are here now? There are 4 ones here. That's an even number. 4 is an even number. So that's the idea of even parity. We will also see another example here. So this is the data sequence given. How do we encode it using even parity? Please check here, how many ones do we have? There are already 4 number of ones. So that is a even. 4 is an even number. So we don't need additional bit here. So the additional bit becomes 0. Or we can do this using this equation or this relation. That is, you XOR each of these bits. 1 1 is 0, 0 0 is 0, 0 1 is 1, 1 1 is 0. So that 0, which is the Q value, you will be adding here as the parity bit. So that becomes the even parity. So this is the encoded data at the transmitter. So this will be sent to the receiver. The receiver will examine it and decide whether there is error or not. So we will see that in the next slide, how receiver will understand whether it is there is any error or not. Okay, so this is the case of even parity. In case of odd parity, we will be doing this step. So suppose a data is given here, we want to encode it using odd parity, then you attach something 0 or 1 here based on 1 minus Q value. Okay, so first you find out Q and then find out 1 minus Q. The whatever value you get, maybe 1 or 0, you attach here. Similarly here, that is the case of odd parity. Okay, so here that's the additional bit ensures that there are even, in case of even parity, or odd number of ones in the code word. In case of even parity, you want to make sure that there are even number of ones. In case of odd parity, you have to make the code word in such a way that there are odd number of ones. Okay, this encoded sequence, after adding the parity bit, is transmitted to the receiver. Now at the receiver, how it is going to decode? To decode, the receiver will calculate the sum of the received bits in the block. That is sum, and when we talk about sum, it is mod 2 addition or XOR operation. And then the sum is 0 in case of even parity, or if it is 1 in case of odd parity, then the data word is the first k bits of the received code word. Otherwise, there is error. So in case of even parity, what we have seen in the previous slide, the sum should be 0 at the receiver. Then, except that, everything before will be the code word. If the sum is not 0, then it means there is an error. We will see what the same example. For example, in the previous slide, we had the data 10110. So we used the even parity on this and encoded it like this, right? We found what is the Q value. Since there are 3 ones here, when we encode it, we have to add one more one here. That becomes the even parity. So this is the encoded sequence for this data. This is the example that we have seen in the previous slide. Okay, now if this data comes to the receiver as it is, then receiver can decode it. But if there is some error instead of this encoded sequence, when it comes through the channel, some error occurs. So instead of 101101, it becomes 100101. That is, this bit has changed. So actually the encoded sequence here it was 1, but due to error in the channel, it becomes 0. Then what happens at the receiver? The receiver will find the sum here. If the sum is 0 in case of even, because receiver while decoding it is going to calculate the sum of the received bits. What are the received bits? These are the received bits. Now we will compute the sum, that is mod 2 operation. 1 0 is 1, 1 and 0 is 1, 1 and 1 is 0, 0 and 0 is 0, 0 and 1 is 1. That means the sum, that is P, is equal to 1 here. But the coding scheme or coding method what we used is a even parity. So in case of even parity, the sum should be 0. But in this case, the sum has become 1. That means the receiver will understand that there was some error in the transmission. Is it so? Yes, because the third bit got changed. We transmitted a 1 here, but when it came to the receiver, that became 0. So there was some error. So because of that error, the parity, which is the sum of all these bits, became 1 instead of 0. That means the receiver will come to know that there was some error in the transmission. Somewhere there was error. Let us also see if there was no error. That means if this was transmitted and it came to the receiver as it is, that means at the receiver you are receiving these bits exactly as it is. Then what happens? The receiver will find the sum of these bits. So what is the sum? 1 0 is 1, 1 1 is 0, 0 1 is 1, 1 0 is 1, 1 1 is 0. So that means p value is 0 if there was no error. So sum is 0 for even parity. That is right in this case. So that means the earlier k bits, all this black color, that was the data. So it will be receiving that data. If p value is not 0, p value is 1, it will say that the received data has error. It will not decode this data because there is some error here. It will detect the error. So the code can detect single errors but cannot correct the errors, since the error could be anywhere. Any of these bits might have changed if there was error. So it cannot detect where exactly the error was, but it can just detect one bit errors. If there are more than one bit error, it's not possible in this scheme. Okay, this is the idea of even parity. So the reverse is applicable for odd parity also. Okay, this is used in serial communication, bit by bit data transmission. Okay, now we will see another scenario of detecting the errors, that is using Hamming distance. So Hamming distance indicates when there are two code words, Hamming distance indicates how many bit positions they differ. So that is the idea of Hamming bits. For instance, we have two code words or two sequences 0 0 and 0 1. These are the two sequences. So let this be C1, this is one code word, and that is another code word C2. In this case, what is the Hamming distance? Hamming distance is, how do you find out that? We will compare the bits this way. For 0 and 0, there is no change. 0 and 1, there is a change. So there is one change in these two code words. Okay, so now another example is 101 and 011. So what is the Hamming distance in this case? So Hamming distance, basically you have to find bitwise the differences. For example, this bit to this bit, what is the difference? There is one difference, right? Because this was 1, this is 0. So there is a change here. So 1 change. Next, 0 and 1, they are not same. So there is another change here. 1 and 1, there is no change because this is 1, this is also 1. So altogether here, there are two differences between these two code words. So the Hamming distance is 2. The first difference is here 1 and 0. Second difference is here 0 and 1. There is no difference in the third position. So the total distance or total number of positions in which they differ is 2. That is the Hamming distance. Okay, so this concept also can be used to detect the errors. So Hamming distance between two code words is simply the number of bit positions in which they differ. So that is what we have seen here. How many positions they have different values. So if the Hamming distance between two code words C1 and C2 is D, the Hamming distance is D. For example, D is 2 here, here it's 1. And C1 is transmitted. For example, C1 in this case, this is transmitted. Then D errors would have to occur for a code word C2 to be received. Okay, so many errors, D number of errors should occur. Then this, in that case only the C2 can be received. If there are more errors, then C2 cannot be received. So that's the idea here. Okay, the Hamming distance between a valid binary code word and the same code word with a single bit error is 1. For example, when we have 2 bits, what different combinations we can have? 0 0 0 1. So in this case, what is the Hamming distance? Hamming distance is 1. So 0 0 is a valid sequence when we have 2 bits. 0 1 is also a valid sequence when you have 2 bits. So this statement is applicable to this scenario here. The Hamming distance between a valid code word and the same code word with a single bit error is 1. So here 0 0, but maybe there is some error and it becomes 0 1. Now there is single bit change. So the Hamming distance is 1. And both are valid sequences when we have 2 bits 0 0 0 1 1 0 or 1 1. These are the 4 possible combinations. Both are valid. Okay, so that's what we have written here. So we have a, just consider 1 bit transmissions. We have a 0 and a 1. I mean, when we send a 0 by mistake, it becomes 1, or due to some error, it becomes 1. Now what is the Hamming distance? Hamming distance is also 1. When you have just 1 bit, it can be either 0 or it can be 1. But if there is error, 0 transmitted becomes 1 or 1 transmitted becomes 0. The Hamming distance is also 1. So a single bit error changes a valid code word into another valid code word. This is a big problem. So when we have just 1 bit, that can be 0 or 1, you send it. At the receiver, if you say, maybe you sent a 0 at the receiver, that becomes 1. The Hamming distance is 1. So receiver, even though that is error, receiver cannot receive it. Or you send a 1 and at the receiver that is received as 0. So Hamming distance is 1. So in that case, the receiver cannot understand whether there was error or not, because both are valid cases when we have one bit. So this is the case of, this is a scenario when both the cases are valid sequences and Hamming distance is 1, then the receiver cannot detect the error. Otherwise, it can try to detect. The same scenario is given here. So we have 0, 0, 2-bit sequences. The 2-bit sequences, when you can have 0, 0, 0, 1, 1, 0, or 1, 1. Suppose 0, 0 you want to send. At the receiver, it becomes 0, 1. So what is the Hamming distance now? Here the Hamming distance is 1, right? Because 0, there is no change. The second bit has changed. The Hamming distance is 1. Or you send a 0, 0. At the receiver, it becomes 1, 0. Now the Hamming distance is how many? Hamming distance is 1. Okay. Now you want to send 0, 0, but at the receiver it becomes 1, 1. What's the Hamming distance now? Hamming distance is 2, right? Both the bits have changed. Hamming distance is 2. So now which of these errors can be detected? See here, if D is the minimum Hamming distance between code words, we can detect up to D minus 1 bit errors. If 2 is the minimum Hamming distance between the code words, then we can detect 2 minus 1, that is 1 bit error can be detected. Okay, so that is the idea here as well as here, because everything here is a valid code word. We cannot detect all the errors in this case. What we need is an encoding where a single bit error doesn't produce another valid code word. For example, here 0, 0 to 0, 1, there is one single bit error, but 0, 1 is also a valid code word. The receiver knows that the data will have 2 bits. So with the 2 bits, we can have 0, 0, 0, 1, 1, 0, or 1, 1. So receiver cannot actually decide where is the error. Okay, because everything is a valid code word with 2-bit sequences. Okay, now we have some definition. First one is a code word. What is a code word? A code word is an n-bit encoded block of bits. So this is basically produced by considering k input bits by adding the redundant bits on that. Next one is a block length. The number of bits n after coding is known as a block length. The code rate is defined as the ratio of the number of message bits to the total number of input bits. For example, code rate R is nothing but k by n. K is the input bits and n is the total number of bits in the encoded sequence. And what is a code vector? Code vector here, n-bit code word can be visualized as n-dimensional space vector. So basically, code vector indicates the size of the encoded sequence. Okay, now the first homework for 25th of November is to simulate the Shannon encoding scheme and Huffman encoding scheme. You may consider any size of the inputs using MATLAB. So use MATLAB to encode the Shannon encoding sequence and Huffman encoding schemes. You may consider any number of inputs or any probability values. Just solve some examples using MATLAB. So we have the deadline for submission on 25th November. So that's the end of discussion for today.